to this double slit, we expected interference, we saw interference, then we turned down the frequency of photons that are shooted out of the laser, such that we basically have single particles now, and nevertheless we get this interference pattern. And the thing is now that we can also do this with all quantum particles. So if we now would not take a laser, but we take an electron beam gun, so this is something we would intuitively describe as a particle, right? So if we point this onto the double slit, we would expect to get this two bumps on the detector. But what we can actually see is, again, this interference pattern, just like in the case with photons. And the same thing with the collapse of the wave behavior applies to the electron case. So that means if we now can say, we detect whether the electron went through the left or through the right slit, then we destroy this interference pattern again and get this classical pattern. Okay, so I think this is something everyone has maybe seen before. For the remainder of this or of today's tutorial, we will talk about a slightly more advanced experiment. And it's called the so-called delayed choice quantum eraser. Before I go to the next experiment, I will have a quick look at the chat, whether there are any questions. Do you record this meeting? No, this meeting is not recorded. Okay, so due to the wrong Zoom link, I'm asked to give a quick summary of what we have discussed so far. Basically, what we've discussed so far only covered organizational stuff, which is all explained on the Moodle. Means please read through the Moodle because everything is on there. And then I explained, I just what I did in this tutorial so far, content-wise, was talking about the double slit experiment, which is a basic experiment from quantum physics to basically show that quantum particles show both particle and wave behavior. And I think since this is something that most high schools cover, I will not explain that again, and I hope that's fine. Okay, will you share your notes that you are taking? I could share my notes, I'm just not so sure whether it's helpful, to be honest. I guess today I will not share it, maybe for tutorials where it's more about actually exercises, I can share if you wish. Is it sufficient if I watch the lecture recording from last year, since we never guarantee for any completeness of last semester's recordings, etc. You can do it. You should check yourself whether the content covered in last year's recordings is the same as the content covered in the lecture script that we upload on the semester's Moodle. Okay, so I guess we can go on with the second experiment, which is a variation of the double slit experiment. It's slightly more involved, but hence maybe also a little bit more interesting, I don't know. Okay, so this, what I'm showing you here is basically a sketch of the experiment, which was actually conducted by researchers in the year 2000. And the overall idea is, I will first sketch the overall idea, and then we will go through this experiment step by step. So the overall idea is that you have a laser beam here, and this laser beam is shown on a double slit here, which is just exactly the same as in the double slit experiment here, right? And then there's a variation to the double slit experiment, because for the double slit experiment, we would now just put a detector, like a screen, behind the double slit. But in this experiment, we basically produce out of each of the photons that would come out of one of the slits, we would produce two entangled photons. So entanglement is a quantum mechanical property. I guess that you have either heard about already or you will learn about it in the lectures, which basically ensures that two photons in this case are dependent on each other. The state of the two photons are dependent on each other. Okay, so this is the first variation. Then what you have is a detector here. So you would have a detector where you want to know whether you have this interference pattern or such a just a diffraction pattern. So the pattern that we would expect from classical particles. But since we now have several photons, we will have some kind of more or less complicated way of extracting information which slit the photon came from. I will explain this in more detail, but what you basically have to know is we have one screen, and basically the photon will arrive at the screen earlier than what happens here, where you basically extract information through which slit the photon that is detected here went through. And spoiler, what you will see is that even if the detector here detects the photon earlier than the information that we can obtain from here, we will see that on the detector, we will only see an interference pattern if we could not, or if we were not able to subtract any information about the path. And by path, I mean the way or the slit through which the photon traveled. Okay. Okay. So this is the major idea behind this, and we will now go through the steps of the experiment in a little bit more detail. Okay. Yeah. So as I said, we have this laser beam here. So this is the laser beam. And if you're interested in like more details about this laser, apparently this is an argon laser, which produces photons of a special frequency. So it generates individual photons of a wavelength of 351.1 nanometers. Okay, so this is what happens here. This is just our light source. Okay, and then we have a double slit. So this is our double slit, and we will call the first or the upper slit A and the lower slit B. Okay? So that means if we now shoot individual photons onto the slit, then it can travel through slit A or slit B. So so far everything is just the same as for the double slit experiment. What happens now is that the photon will travel through a special prism. Okay, how could I? Okay, I take orange for this. So imagine a photon travels through slit A. Then what happens here is that this photon will arrive at this prism, and in this prism, an entangled photon pair is produced. What does it mean? It means that I first have a photon with the initial frequency. So this is just the photon that was produced from the laser. And then in this prism, it will basically be converted into two photons. And these two photons are entangled. And they will have exactly the same wavelength. Oops. And the wavelengths will be in a way such that energy conservation is given, right? Okay, so this is then an entangled photon pair. And the same happens if the photon travels through slit B, okay? So that means, so you can also see it here in the sketch. After this prism, there are two beams basically, or paths sketched in. And now, wait, let me have a look at my notes whether I forgot anything. Okay, so now the two upper photons is what we call the signal photons. Okay, so maybe let me do this in, I don't know, purple maybe? So the two upper photons are these, would arrive at this detector D0. Okay, so this is a detector where we basically want to either obtain an interference pattern or a diffraction pattern. And exactly, so the photons, the two upper photons, they would arrive at the detector and they would be detected by D0, and either you will see an interference pattern or a diffraction pattern on this D0, okay? So, oh, and we call this the two signal photons. So basically these two signal photons are just the same as the two photons, or the photons here in the double slit experiment that are detected on the screen. So due to this more enhanced setup, we now still have access to two other photons. And these are the two photons that go basically, or take the path going downwards, right? So the two lower photons we call the idler photon. So, oops, I think that's not a nice color. Maybe green. So I would just sketch it a little bit in here for the first path. So these are the Adler photons. And these photons are used in order to subtract information or possible information about the path of the photons of the signal photons. Okay? So if you have a look, okay, so maybe I will erase this one here and this one here, and I will now only look at the photon that went through slit, or the photon that is produced by one photon entering slit A, and then there are these two entangled photons produced. One goes up to the detector and one goes now down, and that is what I want to have a look here in more detail. So one photon goes down, will be diffracted here by this prism thing, will be, just let or travel to the beam splitter here. So this is a beam splitter. And a beam splitter is an optical element where you have a 50% probability that the photon is reflected. So if that is the case, it will go this way, and then it will be discovered basically by a detector that we call D4. In the other 50%, in the other cases, we have the photon just traveling through the beam splitter. So it would take this way. Here we have just some mirror, that means it's just reflected. And then we again have a beam splitter, that means we again have a 50% probability that it is reflected. In this case, it would go like here, and then it would be detected by a detector D2. And in the other case, it just travels through the beam splitter and it will be detected by D1. And the same happens with the second Adler photon. So I will just do it for clarification. Let's have a look at the lower Adler photon. It travels like this to the first prism. It slightly changed its path to the first beam splitter. It has a 50% possibility of being reflected. In this case, it is detected by a detector D3. In the other 50%, it will just travel through the beam splitter. It's reflected at this mirror to 100%. Then it travels again to this beam splitter. It has a 50% possibility of being reflected. Then it is discovered by this detector D1. And if this is not the case, then the other 50%, it just travels through the whole beam splitter and it will be detected by D2. So this is a little bit messy, maybe, at first, but basically, if you write down everything very nicely in a structured way, then you will see that there are different possibilities of extracting information where the Adler photons went through. Okay, so that means, let me write this down with green. Okay. So if we detect an Adler photon at D3, so detector D3, that would be this one, then this photon is known to have traveled through slit B. So it can only be that it travels through slit B. If the detector D4 detects some Adler photon, then we know that this photon went through slit A. And in the case that D1 or D2, so this or this detector, detected something, then the photon could have gone through slit A or B. Okay? And as I said in the very beginning, D0, so that would be this thing here, D0 only detects the signal photons, and it actually detects earlier than the other detectors. Okay, so this is just due to the shorter path of the signal photons in comparison to the idler photons. And since each idler photon is entangled to one signal photon, because this is what happens here, right? This is what I explained here at the very beginning. We produce out of one source photon, we produce an entangled pair of photons. Each pair of photons is split into one signal photon and one idler photon. So that means if we know through which slit one idler photon went or traveled through, then we also know that the corresponding signal photon also had to travel through the corresponding slit, because each pair of photons is generated from one photon that traveled through either A or B. And as I said here, either we will detect an idler photon at detector 3 or 4, and hence we know through which slit the idler photon went, and hence we also know through which slit the corresponding signal photon went, or we detect something at D1 and D2, and then we don't know any information about which path the two photons went through. And detector 0 will always detect something, right? The question is now what happens, or is there a difference, just like here in this double slit experiment, is there a difference whether we could extract information about the slit through which the signal photon traveled through? And yes, actually, there is a difference. So what is done for the data analysis is that we have this thing here called a coincidence counter, and it counts whenever 0 detects something and D1, 2, 3, or 4. Okay, and of course you also have to get rid of this time delay due to the different path lengths. So I said that D0 would always count a little bit earlier. You have to get rid of this time delay, but then what you can say is if a photon is detected at D0, so this will always happen, D0 will always detect a photon, or each photon basically. And then if you also detect something, for example, at D3, that means that the entangled photon pair, of the entangled photon pair, the idler photon went through slit B, and therefore we also know that the photon that was detected by D0 also went through slit B. Okay, and what you now do is you basically analyze the coincidence rates. So R01 just means that a photon pair was detected at detector 0, so this will always happen, and detector 1. And what you will see is that there are two different patterns that you will see depending on the combination. So either you see something that corresponds to an interference pattern, or you will see something that is just like a bump. So this will look like a diffraction pattern, right? And what you then can see is that the interference pattern will occur if the Adler photon was detected by either detector 1 or detector 2, which is the case when we don't know whether the Adler photon and therefore also the signal photon went through slit A or B. That means in this case, we don't have any information about the path that the photon took. And therefore, we did not basically measure the slits, and therefore we have this interference pattern. It's just like in the double slit experiment when we see this interference pattern, as long as we don't have any information through which double slit the thing went through, the photon. And in the other case, if we have the detector 3 or the detector 4 detecting the Adler photon, then we only have a diffraction pattern, and this corresponds to the case when we basically know that the Adler photon either took the slit A or slit B. So this is just the same again as here in the double slit experiment, where we destroy the interference pattern and therefore the wave behavior by detecting which slit the photon took. Okay, let me have a quick look at the chat because it was quite active. Okay, let me see. Okay. Okay, what's the difference between signal photons and entangled photon pair again? Yeah, that's a good question. Okay, so you have one photon traveling either through A or B. So this is here in the very beginning. And then this photon, after the double slit, the photon will arrive at some prism, this thing here. And in this prism, this thing here happens. So in this prism, one photon is converted into an entangled photon pair, okay? That means one photon goes in and two photons go out. And these two photons, are just a pair, and you know both photons arise from an original photon that either came through A or B. And now the signal photon is just the upper part. So in this thing here, this upper part would be the signal photon. The lower photon will be the Adler photon. Okay. I hope that was now clearer. I'm not sure if I got that, but what was the motivation behind this experiment? The motivation behind this experiment is to show that, in this case, laser or light can behave as waves. That means they show interference pattern when they interfere, or particle behavior. That means you just see a diffraction pattern. And whether they show their particle behavior or their wave behavior depends on the information that you extract. So in this experiment, you will see interference if you cannot say anything about the path, about the slit A or B that your photon took, as soon as you can extract information about this, as soon as you can say, oh, the photon took the upper slit A or the lower slit B, you will not be able to see any interference pattern anymore. The interference behavior will collapse, the wave behavior will collapse, and you will only see a diffraction pattern. And the diffraction pattern is what you would expect from a classical particle, for example. The point is just that in quantum, we have this dual picture of a particle or a quantum particle showing both particle behavior as well as wave behavior. And this applies to, for example, photons, it applies to electrons, it applies to all kinds of particles, and the larger the particles become, the less the effect will be such that we seem to only see classical behavior. But basically this applies to all quantum particles. What's the name of the experiment? It's the delayed choice quantum eraser. What do the curves mean again? So the supplied. Okay, so this is a screenshot from the paper that is also linked on the tutorial sheet. And basically what they did is they only analyzed the data for the first, for these 3 cases. So when you detect the Adler photon on detector 1, 2, or 3, and then they basically just said qualitatively the pattern for the case when you detect an Adler at a photon at detector 4 should just be the same as for the case when you detect it at detector 3, which is because if you detect it at detector 3, the Adler photon, you know immediately the Adler and the signal photon both went through slit B. Hence, you will have this diffraction pattern since the wave behavior collapses. And it should just be the same if you detect it at detector 4, where you immediately know that both photons went through through the slit A. So it just means that this graph down here, the supplied one, was not actually produced by actual measurement data, I guess, but it's just like, it just, physically it should be the same. Why do we need D0 then? I get the rest, but it's a bit unclear what D0 contributes to the result. Okay, so D0 is, that's a good question. D0 is the photon that actually interferes. So the detectors D1, D2, D3, and D4 are not the photons that interfere. These are the detectors that will tell you whether the Adler photon went through slit A, slit B, or whether we cannot gain any information. And no matter whether we can or could gain information or not, D0 will always detect the photons, and the photons will either interfere or not. The interesting thing is that detector D0 will detect all these photons that will interfere or not. And in time, this happens prior to the detection of the Adler photon. So that means basically detector D0, basically everything is already detected. And then after some time, so I mean, that is now exaggerated, but basically what you can think about is after some time, the Adler photon is detected at D1, D2, D3, or D4. And that means that although the detector D0 has already detected everything, the information about whether we can extract the information about the path or not is obtained after D0 has detected anything. And nevertheless, if, for example, the idler photon was detected in time later at D3, then we know later that both photons had to go through slit B, and hence at detector D0, you will not see any interference pattern. I don't know whether this is clearer now. If not, just let me know again. Could you maybe explain the purpose of the signal photon for the results again? And maybe the dimensions of the RXX result graphs. Okay, so the signal photon, I think this is basically what I just explained again, what D0 does. It's just again, it's the photons that actually interfere or not interfere, depending on whether we have information or not. And this here, the graph here, shows the coincidence rate. So, okay, maybe I should have, I think I did not say that, but Y is the coincidence rate, and in X direction, this is basically, this is kind of sketched here, but it's like the detector, the width of the detector. So maybe I show it up here in the double slit experiment. You have a screen. Oopsie. You have a screen, right? I just copy it. And then you have the width X, and depending on this X, the detection rate is basically plotted. So this is this dimension here, and then you can see this interference pattern. It's just the same here, just with D0, okay? Okay. Do we need to know the setup or just the result that we do not know the final path in case of interference, and when we know the path there is diffraction? I don't, I think I don't understand this question. Like, I think I don't understand the sentence. But I can maybe shortly summarize again. If detector D0 detects interference or not, it detects interference if the remaining detectors could give us information of which slit the photon went through. If the remaining detectors, so D1 to D4, did not give us any information, then the corresponding photons, of which we don't know the path, will interfere. Maybe this addressed the question, I'm not sure. Could we measure D0 before one of the others provide a signal? Yes, and this is what happens because D0 has the path of the photon that travels to D0 is shorter than the path of the photons that travel to D1 to D4. Hence, the detector D0 detects earlier in time. Does D3, D4 have to detect the photons before D0 to see these results? And someone already explained what I just said for the question before. D0 always detects first. So even if the detection that causes the wave function to collapse happened later, the wave function has already collapsed on D0. Exactly. You can imagine that D0 is a detection screen where we can see a pattern while the others are just binary detectors. Yes, exactly. That's correct. So if I understand correctly, the interference pattern shows up on D0 during the time it takes the idler photon. No, that's not correct. Okay, sorry, I have not read out the whole question. The question was, so if I understand correctly, the interference pattern shows up on D0 during the time it takes the idler photons to be detected, and then it turns to diffraction. And the answer is no, this is not correct. The detector D0, what is detected by D0 cannot be changed afterwards, of course. But you will only be able to extract the coincidence rates after the idler photons have been detected, right? And it's not that D0 shows the interference, like D0 itself shows interference or not. It's just that if you take the coincidence rates of D0 and the corresponding idler photon, then you will see interference or not, okay? So this is just a plot of photons, of the signal photons that correspond to the idler photons that went, or that were detected by detector 1. Yes, and then someone posted the Wikipedia link to this, and yeah, I can also recommend just reading through the Wikipedia article again if anything was unclear, because they also explain it in very detail. And yeah. Okay. Okay. So basically, this was it for today's tutorial. So as I said, today it was more like some smooth introduction to quantum in general. I think from next week on, there will be more exercises. So not such a focus on experiments, but more exercises that are actually related to what you also learn in the lecture for quantum computing. But yeah, do you have any further questions? If yes, you can raise your voice or just put them onto the chat. Okay, so I think this is not the case. Then I thank everyone for attending this tutorial, and we will see each other next week, Monday. I will stay for another 5 minutes if any later questions should come up, but you are welcome to just leave the room now. Thanks and goodbye.